In order to facilitate our continued discussion of martingales, we're going to backtrack a little bit now to a topic from pure measure theory that we skipped earlier on in the course: uniform integrability. Given a probability space, or more generally a finite measure space, a collection of L1 random variables is called uniformly integrable if the tail expectations are uniformly small over the whole collection. That is to say, if we look at the L1 norm of the random variable on the event that it stays bigger than some constant a, and look at the supremum of that over all of the random variables in the collection, then that supremum should go to 0 as a goes to infinity. Of course, for any one fixed L1 random variable, this quantity here will tend to 0 as a goes to infinity by condition of it being L1. Here, we're insisting that the supremum of all of those still goes to 0. So that is to say, the tail expectations are uniformly small. Let's look at some examples of uniformly integrable collections of random variables. Suppose that lambda is a set of L1 functions that are all dominated by some fixed L1 function. Well then, if we consider this tail expectation, the expected value of the absolute value of x on the event, that x is bigger than or equal to a in absolute value, well, let's look at that event. The event, the absolute value of x is greater than or equal to a. Since g is greater than or equal to x, it therefore follows that g is greater than or equal to a on that set. In other words, the event that x is greater than or equal to a in absolute value is contained in the event that g is greater than or equal to a. So that means that this indicator function here is bounded above by the indicator of the event that g is greater than or equal to a. And similarly, by assumption, this absolute value of x is bounded above by g. And so that shows, since this is true for every x, that the supremum over all x in that set is less than or equal to the tail expectation for g. But since g is in L1, that goes to 0 as a goes to infinity. And so that shows us that this collection, lambda, is uniformly integrable. Here's another very useful example. Suppose that our collection lambda is not just in L1, but is actually contained in LP for some p bigger than 1. And moreover is LP bounded, not just that the LP norm of each of the elements of lambda is finite, but that the supremum of them is finite. All their LP norms are less than or equal to some fixed constant. In that case, this set lambda will actually be uniformly integrable. And here's why. If I consider the tail expectation for some a, well, on the event that x is greater than or equal to a, x over a is greater than or equal to 1. And so if I consider the expected value here of x times that to the power p minus 1 on the same event, then since this is greater than or equal to 1, this quantity here will be less than or equal to that quantity there. But of course, that's just equal to 1 over a to the p minus 1 times the expected value of just x to the p. Now, by assumption, this is uniformly bounded, and since p is greater than 1, this tends to 0 as a goes to infinity, and so this tends to 0 at a uniform rate as a goes to infinity, which shows that this set is uniformly integrable. And as a final simple example, note that any subset of a uniformly integrable set is uniformly integrable, since that just means we're taking the supremum over a smaller set. And of course, if this limit of positive quantities goes to 0 over this larger supremum, it will also go to 0 over a smaller supremum. Now, thinking a little bit more about this LP example here, it was certainly necessary in the proof that the set be LP bounded. One might wonder if we could do the same thing with p equal to 1. Is it enough for a set to be L1 bounded in order for it to be uniformly integrable? Well, the answer to that is no, as we'll see later in this lecture, but the reverse condition is certainly correct. Any uniformly integrable set must be L1 bounded. And here's why. If lambda is a uniformly integrable set, then by assumption, this tail expectation tends to 0 uniformly. So in particular, that means that we can find some large number a, such that this is less than or equal to 1. Therefore, for any x in our collection lambda, if we take just the L1 norm, the expected value of the absolute value of x, well, we can express that by integrating over the two complementary sets. The set where x is less than a in absolute value, and the set where x is greater than or equal to a in absolute value. Now, just breaking up that expectation, now for the fixed a that we've chosen, this is less than or equal to 1. But on this set here, x is less than or equal to a, and so this expectation is less than or equal to a. Therefore, for every x, we get that the expected value of the absolute value of x is less than or equal to a plus 1. And there's our uniform L1 bound. Now, to see why the converse of this is false, it's useful to show that uniform integrability is actually equivalent to a different uniform continuity type condition in terms of these measurable functions. We call a collection of L1 random variables uniformly absolutely continuous if we have the following measure-theoretic continuity condition. For every epsilon, we can find some delta such that for every measurable subset whose probability is less than delta, the supremum over the whole set of the expected value of the absolute value of x on the event B is less than epsilon. You can see that uniform integrability falls into this kind of form here, where we're looking only at defense B of the form x being bigger than or equal to some constant in absolute value. Now, it's useful to write uniform absolute continuity in a slightly more concise form if we consider the function of delta, which is the supremum of the set of all of these numbers, expected value of absolute value of x on the set B, for all sets B whose probability is less than delta and all x in lambda, then that function of delta tends to 0 as delta tends to 0. That's equivalent to this formulation here. We're now going to show, using both of these formulations of uniform absolute continuity, that uniform integrability is equivalent to uniform absolute continuity together with the condition L1 boundedness. That's the proposition right here. And so let's go ahead and proceed to prove it. First, we'll assume that lambda is a uniformly integrable collection. We want to show that it's uniformly absolutely continuous. Well, fix any a, positive number, fix any measurable set B, and take any x random variable in the collection. Then if we look at the expected value of the absolute value of x given B, we can, as we did in the previous slide, break up that expectation over the two complementary events where x is greater than or equal to a in absolute value and where x is less than a in absolute value. Now, for this second term, on the event where x is less than a, we have that this expectation is just less than or equal to a times the probability of b. Therefore, if I take the lim sup of all of those quantities where x ranges over lambda and b ranges over all probability less than delta sets, well, that's less than or equal to the lim sup of this plus the lim sup of that. Now for the second term here, the lim sup of this, that's going to be less than or equal to the lim sup of this. But that lim sup is just 0. And so we only have to contend with the first term here. And there, we'll bound above by ignoring the condition that we're on the set B. But without that condition, this lim sup over delta just turns into the supremum of this quantity here. And by the assumption of uniform integrability, that tends to 0 as A tends to infinity. And so what we find is that this quantity here is less than or equal to something which goes to 0 as we vary the parameter a. But a was our choice in the problem. So that means that we can make this less than epsilon for any epsilon by choosing a sufficiently large. Thus, this goes to 0, and so we've shown uniform absolute continuity of our collection. We also know that our collection is L1 bounded, because, as we showed, any uniformly integrable set is L1 bounded. Now for the converse, we'll assume that our collection is uniformly absolutely continuous and L1 bounded. It's important to note that uniform absolute continuity does not imply L1 boundedness. It's a local condition. So let's let K be an L1 bound for the set. Again, we'll fix a positive A and consider any random variable x in our collection. Now we'll use Markov's inequality, which tells us that this probability is less than or equal to the expected value of this divided by this. The expected value of that is just the L1 norm, and all those L1 norms are bounded by this k. So we get that the probability of this event is less than or equal to k over a. Well, now we use the assumption of uniform absolute continuity, which tells us that for any fixed epsilon, we can choose a delta so that for all measurable sets of probability less than delta, the supremum of this expectation here is less than epsilon. What we're going to do is take this set B to be of this form. And we just need to choose our A so that therefore the probability of that event will be less than delta. Of course, this tells us how we should do that. If we set A equal to, let's say, 2k over delta, then that means that with B equal to the event that the absolute value of x is greater than or equal to that A, the probability of B will be less than or equal to k over A, which is delta over 2, which is less than delta, and therefore by the uniform absolute continuity, it follows that the supremum over all x in the set lambda of the expected value of the absolute value of x on the event B, which is the event that x is greater than or equal to A, is less than epsilon. But that's precisely to say, again, due to the fact that this is easily seen to be a decreasing function of A, that the limit as A goes to infinity of this quantity here is 0, which is to say that lambda is uniformly integrable. The uniform absolute continuity formulation of uniform integrability, together with the assumed L1 boundedness, is useful for proving local properties of uniformly integrable sets that would otherwise be hard to see directly from the definition. For example, translations of uniformly integrable sets are uniformly integrable. If lambda is a uniformly integrable set of L1 functions and x is any fixed L1 function, then lambda plus x, the set of all random variables of the form y plus x, where x is in lambda, is also uniformly integrable. Actually, we could take another uniformly integrable set of random variables here and look at the set of sums of those, and I would get a new uniformly integrable family. But this translation result is all we'll need in our lecture today. The proof is as follows. We will use the equivalence to uniform absolute continuity. Lambda is assumed to be uniformly integrable, therefore it's uniformly absolutely continuous. And so we can choose for any epsilon some delta 1, so that for all probability less than delta 1 sets, the expected value of the absolute value of y on the set B is less than epsilon over 2 for all y in that set. Now similarly, the singleton set x is uniformly integrable, since it's just one L1 function, and the condition for uniform integrability is just exactly satisfied by an L1 function. Therefore, it is also uniformly absolutely continuous. And so we can do the same thing for that given epsilon. We can choose some delta 2, so that for all probability less than delta 2 sets B, this expected value is less than epsilon over 2. So now let's look at sets of probability less than delta, where delta is the minimum of delta 1 and delta 2. If we take any such measurable set, then the expected value of the absolute value of the sum of x and y on the event B by the triangle inequality is less than or equal to the expected value of the absolute value of x on B plus the expected value of the absolute value of y on B. But since delta is less than delta 1 and delta 2, by the uniform absolute continuity construction above, this will be less than epsilon over 2 plus epsilon over 2, which is epsilon. So that shows us that this collection of random variables here is uniformly absolutely continuous. But we also know that this set is L1 bounded. Again, by the triangle inequality, this will be less than or equal to the supremum over lambda 1 of the L1 norm plus the L1 norm of x. And this is finite, and so that's finite. And so therefore I get that this collection is uniformly absolutely continuous and L1 bounded, and therefore by the previous proposition, it is uniformly integrable. Now that little result allows us to prove the following theorem, which tells us that what uniform integrability actually means is exactly the gap between L1 convergence and convergence in probability. Here's the statement, and this is the Vitali convergence theorem if you're looking for a name. Given any collection of L1 random variables and any measurable random variable x, then the statement that random variable x is in L1 and xn converges to it in L1 is equivalent to the statement that the family xn is uniformly integrable and xn converges in probability to x. By the way, there's an LP version of this theorem as well, which we can get directly from this one just by taking pth powers everywhere. We're going to stick to the L1 version since, as we saw on the first slide, uniform integrability for LP bounded functions is pretty much automatic. It's the L1 case that is most interesting and challenging. So let's prove this. We'll start with what should be the easier direction, that L1 convergence implies uniform integrability and convergence in probability. Well, half of that was proved early on in this course in lecture 13.1, that L1 convergence implies convergence in probability. Now we need to show that L1 convergence implies uniform integrability, and this is trickier than you might think. We're going to use the result that we just proved as a consequence of the equivalence between uniform integrability and uniform absolute continuity together with L1 boundedness. So let's let yn be the difference, xn minus x. Our assumption in this direction of the theorem is that this tends to 0 in L1. Now fix any index n that is finite and look at the supremum that we need to look at to prove uniform integrability, but here we're going to be looking at yn instead of xn. Well, this supremum is less than or equal to the supremum of this quantity over the finite number of n's less than that capital N that you chose, maximized with the supremum over all of those later on. This collection here is a finite collection of L1 random variables, and any finite collection of L1 random variables is going to be uniformly integrable. For example, you could prove that using the first example. There is a uniform dominating L1 function for all of these. Just take the maximum of them. And for this quantity here, let's just be fairly blunt and bound this by the supremum of just these L1 norms. So what we get from that is that the limit we're interested in is less than or equal to the limit of this plus the limit of this, because the maximum is less than or equal to the sum for two non-negative sequences. And the limit of this is going to be 0 because these are uniformly integrable. And therefore, we just get that the limit of this is less than or equal to the limit of that, but ignoring the a, that's just giving us the bound here, supremum over all n bigger than or equal to capital N. But that capital N was an arbitrary choice that we made, and notice that since the sequence yn converges to 0 in L1, this goes to 0 as capital N goes to infinity. But that means that we can choose capital N large enough so that this bound we get here for this limit is as small as we like, and therefore this limit goes to 0. So putting those together, what we've shown is that the sequence yn is uniformly integrable. But what about the sequence xn that we were originally interested in? Well, that sequence is a translate of the sequence yn by a fixed L1 function. And so by our corollary on the last slide, it follows that xn is uniformly integrable as well. So that shows us the forward, easier direction of the Vitali convergence theorem. For the converse, we only know that xn converges in probability to x, and that the xn sequence is a uniformly integrable family. We want to conclude that we therefore get L1 convergence. We could think of this, by the way, as a big strengthening of the dominated convergence theorem, since, as we saw, having a uniform dominating L1 function implies uniform integrability. So this is an even weaker condition than the convergence in probability form of the dominated convergence theorem that we proved earlier. So suppose that we have those conditions there. Well, if I fix any a positive constant, and I look at, again with yn equal to the difference here, yn times the indicator of the event that the absolute value of yn is less than a, well, this is a sequence of functions that is bounded above by a, which is a L1 function. And therefore, by the dominated convergence theorem, the convergence in probability here implies that we get convergence of this sequence in L1 to 0. But one more time, breaking up as we have before, we take the L1 norm of yn, which is what we're interested in, and break that up over the event that yn is less than a and the complementary event that yn is bigger than or equal to a in absolute value. Well, we just showed that this tends to 0 as n tends to infinity. And on this side here, that is, of course, less than or equal to the supremum over all k of the expected value of yk times the indicator that yk is bigger than or equal to a. And uniform integrability tells us that that goes to 0 as a goes to infinity. Well, again, a was an arbitrarily chosen positive constant here. So what that shows us is that the lim sup, as n goes to infinity, of this side is less than or equal to 0 plus any small constant that I want over here, because I can choose a large enough to make this as small as I want. Therefore, the lim sup of this is 0, which concludes the proof. Now, why am I telling you about all of this now, in the midst of the beginning of our discussions of martingales? Well, the reason is that uniform integrability is a property that all regular martingales have. And in fact, that's the distinguishing feature that can tell us when a martingale will fail to be a regular martingale. So here's the proposition that shows us why that's true. If p is any constant bigger than or equal to 1, of course, we'll be most interested in the p equals 1 case here, and x is any fixed LP function, then if I consider the following collection of LP random variables, that is, the collection of all possible conditional expectations of x onto any sub-sigma field of the base sigma field F for our probability space. That collection is LP bounded and uniformly integrable. Now, this is a no-brainer statement in the case where p is bigger than 1. First of all, we know that conditional expectation is an LP contraction. That shows us that this family is LP bounded, and we know that any LP bounded collection with p bigger than 1 is automatically uniformly integrable from the first slide of this lecture. So now we're interested only in the case p equals 1, which is the harder case. Well, in this case, we're going to need to use the monotonicity of conditional expectation, not just in norm. The absolute value of the conditional expectation of a random variable is less than or equal to the conditional expectation of the absolute value, as we proved earlier. And from that, we can deduce the following. If I take this quantity here, which is what I need to consider the supremum of over all g to show uniform integrability here, by this inequality here, that's going to be less than or equal to the expected value of the conditional expectation of the absolute value of x on the event that the absolute value of the conditional expectation is bigger than or equal to a. And here's the key point. This random variable here is g measurable, and therefore so is this random variable, which means that we can bring it inside this conditional expectation. But once it's inside, we're doing a double conditioning, and of course the expected value of a conditional expectation is just the plain old expectation. Now, how do we deal with this? Well, we're going to appeal to the equivalence between uniform integrability and uniform absolute continuity in the L1 bounded context. That means that we want to look at this event here and how its probability varies as a goes to infinity. That's easy to check by Markov's inequality. This probability is less than or equal to the expected value of this divided by this. But again, using this monotonicity property here, that is less than or equal to the expected value of the conditional expectation of the absolute value of x. And that's just equal to the expected value of the absolute value of x. And that, of course, tends to 0 as a tends to infinity. More importantly, it does so uniformly in G. Okay, so that shows us that the probability of this event here gets arbitrarily small, and since the singleton family containing just the random variable x is uniformly integrable and therefore uniformly absolutely continuous, it follows from the definition of uniform absolute continuity that this must also tend to 0 uniformly in G as a tends to infinity. In other words, the limit as a tends to infinity of the supremum over all sub-sigma fields G of the quantity that we're interested in here, the expected value of the absolute value of the conditional expectation of x given G, on the event that that absolute value of conditional expectation is bigger than or equal to a. That whole supremum limit is 0, which is exactly the statement that lambda is uniformly integrable. In particular, we see from that if xn is any regular martingale, which means remember that xn is just given by conditioning some fixed L1 random variable by the filtration fn, then xn will be uniformly integrable, because this collection of random variables is certainly a subset of this lambda, and any subset of a uniformly integrable family is uniformly integrable. Last time we opined on the fact that the symmetric random walk on the integer lattice is not a regular martingale, even though it's a martingale, because it's not L1 bounded. But this gives us a sharper condition. Regular martingales are not only L1 bounded, they're also uniformly integrable. And that means we can find martingales that are L1 bounded, but still not regular. And here's an example, in fact, of the form that we saw at the end of the previous lecture. Let Zn be a collection of IID random variables that are all shifted uniform distributions. That is, they're all uniform on the interval from 1/2 up to 3/2. The reason that I've made that shift is so that the expected value of each Zn is 1/2 plus the expected value of a uniform, which is also 1/2, so that's 1. Also, note that all of these Zn's are greater than or equal to 0, in fact, greater than or equal to 1/2. So as we saw last time, that means that if I take xn to be the progressive product of the Zn's, it is a martingale. And moreover, the independence tells us that the L1 norm, the expected value of the xn's, is going to be, well, since they're positive, just the expected value of xn. That's the product of the expected values of these guys, which is just 1 for all n. Therefore, this is an L1 bounded family of random variables. Is this martingale a regular martingale, though? If it is, that means it must be uniformly integrable by what we just proved. Let's check to see if that's possible. Suppose that we can find some L1 random variable x so that xn is the conditional expectation of x given fn for some filtration fn. Since each xn is non-negative by the monotonicity properties of conditional expectation, it also must follow that our x is a non-negative random variable. Well, now, let's use some tools we developed earlier in this course. This is a product. Let's turn it into a sum by taking the logarithm. There's no problem doing that because all of these are strictly positive. They're all bounded below by 1/2. And if I take the logarithm of that product, it turns into the sum of the logarithms. If I divide that by n, actually I should probably divide by n plus 1, but it won't matter here, of course, since the ratio of n plus 1 to n goes to 1, then this is something which is well set up for the strong law of large numbers. If I knew that these were all L1, then I would be able to apply the strong law of large numbers to say that this converges almost surely to their common mean. Well, let's compute that common mean. The logarithm of each term zj, which is the logarithm of 1/2 plus uj, where uj is a standard uniform random variable on the unit interval. Well, first of all, that random variable, it lives in the interval from log 1/2 up to log 3/2. Now this is some negative number, it's negative 0.693, but whatever it is, this is some fixed bounded interval. So these are bounded random variables, and therefore they're certainly L1. So that means that the strong law of large numbers does apply, and this will converge almost surely to whatever the expected value of each of those terms is. Of course, we can compute that with some calculus. That's going to be the integral from 0 to 1 of the log of 1/2 plus u du, since the density of the random variable u is just the indicator function of the unit interval. And I'll spare you the calculus, but you can work out the exact value of that, and it works out to be approximately minus 0.045. So this converges almost surely to a constant, which is approximately minus 0.045. All that I care about from that is the fact that that is negative. Because what this is saying is that this 1 over n times the log of xn converges to something negative. It follows from there that the log of xn is pretty close to this number times n, which means that xn is pretty close to the exponential of this negative number times n, and it follows from there that xn converges to 0 almost surely. Since it converges to 0 almost surely, it therefore converges to 0 in probability. Now, if xn were a regular martingale, then by what we've shown, that would mean that it's uniformly integrable. And by the Vitali convergence theorem, the convergence in probability to 0 together with uniform integrability would imply that actually xn converges to 0 in L1. But that turns out to tell us something about the original random variable x, which we're assuming we get xn by conditioning. If I compute the L1 norm of that x, which is just the expected value of x, since x is non-negative, well, of course, we can compute that by double conditioning. And this, by definition, is xn, so that tells us that the L1 norm of x is the same as the expected value of xn. But xn, we just showed, goes to 0 in L1, which means, of course, that its expected value tends to 0 as n goes to infinity. Of course, there's no n on this side, and so that just tells us that this L1 norm is constantly equal to 0. That is to say, x is 0. But that means that xn, which is the conditional expectation of x on fn, is just 0 for all n. But that's not true. The expected value of xn is 1 for every n. It certainly can't be the 0 random variable. So that shows us that this martingale, xn, is not a regular martingale. And it also gives us a nice example of how L1 boundedness does not imply uniform integrability. There are non-negative L1 bounded martingales that are not regular. Now later on, as the capstone result for our whole discussion of martingales, we're going to show that the converse of this is also true. If xn is any L1 bounded martingale that is uniformly integrable, then it is a regular martingale. That will follow from the martingale convergence theorem that we'll get to in a few lectures.